Hi, my name is Ramesh Harjani. I'm from the University of Minnesota, and today I'd like to talk a little bit about analog circuit design. So, in particular, I'm going to talk about connections and things of that ilk. So the talk is really about analog circuit design, but it's organized in a certain fashion. I'm going to talk about analog is, you cannot stay in analog alone. There's a pendulum of swings that you have to deal with, going from digital to analog and back to digital and so forth. And I'm going to use a couple of icons in this. You can see the D on the left-hand side, and you can see the red A. And when I have an A in my slides, it's talking about analog. And the next thing I want to mention in this presentation is about cross-pollination of ideas and connections that we have to make or people have made to be successful in this area. In particular, I'm going to talk about connections between analog and digital, analog and communications, and analog and signal processing. So let me start off with my first observation. When we think of communications today, we think that digital communication is a really modern technology. And it resulted from Shannon's communications theory. But in fact, digital preceded analog communications. And in particular, if you think about the Morse code picture that I see in the right, this started in the 1844s. And it was basically a 1 and a 0, your dot and a dash in digital communication. And we shouldn't relegate this to an old technology in the sense, because it enabled a lot of new technology. In fact, when we talk about full duplex today with your cell phones and being the next technology for wireless communication, Edison did full duplex with telegraph in his quadruplex. Edison also had a universal stock printer where all the mechanical printers at the different stock monitoring offices all synchronized at the same time. And in fact, what we know of Nyquist theory in 1924 was established around the telegraph. The actual document was certain factors affecting telegraph speed. And this was a precursor to both switching theory and computers, and precursor to the telephone from Bell Labs. And when we went to Bell Labs and the telephone, the breakthrough between telegraph and the telephone was basically to stop thinking digital and to start thinking analog. So when we think of analog being old, it really was the new technology when the telegraph was introduced. So here's the first analog communication that happened, and it was done by Reginald Fessenden. He actually worked under Edison for a little while and then left very quickly. And he, like lots of folks are called the father of radio, but the first analog communication was actually done by Fessenden. So the thing he talked about was like 1, 2, 3, 4, is this knowing where you are, Mr. Thiessen? If it is, telegraph back and let me know. So that was the actual communique that was to be telegraphed back. This was done in the December of 23rd, 1900. It's the first wireless voice communication. A patent was filed for this in 1901 on AM modulation. And the AM modulation was very different from what we see today. If you look at the bottom left, you see a picture of a generator. So a generator can generate DC or AC. In this case, it was generating a 17.2 kilohertz AC signal. So this, as you understand, the antennas for this can be fairly large. It was a 1.9 kilometer antenna. And this is not the exact one that was done by Reginald, but this is one that still exists today. It's in Sweden, and it's a World Heritage Site that is operational and it operates a couple of times a year. So the two pictures for the sending circuit and the receiving circuit are shown at the right bottom. And so what we started with digital telegraph, then we went on to analog communication, and I want to show you that pattern again and again. In this case, we're starting with analog. So if you look at the first filters, the LC ladder filters, we started with LC ladders, and in discrete form, they were really quite impressive, but inductors were hard to integrate. So the first generation of this were in the form of active RC filters. On the right-hand side, you see some equations that show you the parameters for this filter, including the transfer function shown on the right-hand side. where S is the filter pole, and the gain of the circuit is basically from operational amplifiers we know is minus R2 over R1. But the pole location shown in blue on the right hand side, we can see is a function of both the resistance and the capacitance. And they are, so when there was a temperature or process variation, they vary independently such that the pole location was never possible to fix. The other problem was resistance are physically large on chip, and so we came up with the next step, which is we're now looking at not analog continuous time, but we're looking at discrete time analog. So the understanding of going from the S domain to the Z domain, which required an understanding of digital signal processing, but as applicable to analog signals. So the first switch capacitor filter was proposed by David Fried in 1972. And then simultaneously, around 78, Professor Dave Alstott and Professor Ken Martin simultaneously proposed a parasitic insensitive switch capacitor circuit. On the bottom, you see the switch capacitor circuit. And in this circuit, if you look at C1R, which is a replacement for R1 from the previous picture, and C2R, which is a replacement for R2 in the previous picture. Now from this, what we see is that the pole location is now a function of ratio of two capacitors and a clock frequency. And the ratio of two capacitors can be matched very accurately to 0.1%. And the speed can be, since they are taken out from crystal clocks, they can be very accurately, precisely generated. We also see that the gain of the circuit is a capacitive ratio, which is again matched very well. The last part I want to point out in this circuit is the R equivalent circuit is the amount of charge that you transfer, the average charge, voltage over charge that you have, which is 1 over Fc. So what we see here is that the pole frequency has now become process and temperature independent. For this to be successful, we needed to have an understanding of the Z domain. Now, the other thing that's interesting is, if we want to go to low powers, you have to make the resistance large. So physically, on chip, that would mean very large area. But here, when we're building it out of switch capacitor circuits, when we are trying to go to low power, we actually have to make the resistance large. But as seen on the right-hand side equation here, that means making the capacitor smaller. So low power actually meant very small, low-cost circuits. To make this connection, what I'm trying to emphasize in this talk is to make this connection, we had to now think in the Z domain and come back to living with analog signals. The same thing happened with another topic, and this is a topic called complex filters. So we traditionally think of filters being real signal filters in the sense that they're continuous time analog filters, and Hermann Helmholtz in 1847 talked about the energy conservation of the complex filters, or of filters in general. And then we had network filter synthesis proposed by Yukwin Lee in 1930, after he had conversations with Vannevar Bush. And I want you to keep this name in conscious of Vannevar Bush. So the first digital complex filters were known by the digital folks in 1968. And in fact, people in analog, Martin Snellgrove, who was Ken Martin's student, did his PhD in this area in 1982. So roughly 68, 78, so about 14 years later, the analog community got to know about complex filters, but they got lost. And they were rediscovered by Jan Krolls in image received transceivers in 1995. The basic idea for complex filter is that you can take a real filter, which has one input, one output, and then you move the frequency in the frequency domain laterally. And this is accomplished by having two inputs and two outputs as shown in the center. And the design that is proposed in the center was out of Martin's work. The work that came out of Jan Krolls in 1995 is what is shown as the polyphase filter on the right-hand side. So the point I wanted to make here is that digital complex filters were known in 1968, but only rediscovered by the RF and circuits community in 1995, and this is because we don't do this cross-pollination as much as we should. I see something similar along the line of data converters. If you look at analog and digital converters, we have different kinds of converters: flash, subranging, pipeline, SAR, and incremental converters was proposed by Roberts in 1987. Now, if you look at the picture on the bottom left, we see here in this integrator, in this particular data converter, there is an integrator, there is a comparator, and in the feedback loop, there is a signal that provides a digital to analog conversion of the value taken out from the comparator. So if you think about this, this is exactly what goes into a sigma delta converter, except the thinking at that point was purely in the time domain. And so for a 16-bit converter, it required 2 to the power 16 counts, which is 65,000 counts. Now, what we see here is that this is identical to a sigma delta converter, but we are still thinking in the time domain. So I should point out that Roberts, in a few years later, went to a second order up-down counter and dropped the counting to 256. But the transition to sigma delta converters came from a different thinking process. And we see a lot of research that was done in sigma delta converters around 1980s, particularly Candy and Bob Adams. And here's the fourth order. If you use a fourth order 16-bit sigma delta converter, your oversampling ratio now drops to 32 rather than 65,000 as we saw in the previous case. So if you look at the picture in the middle, you see a sigma delta converter which has a filter, an integrator, a quantizer, A to D converter, and a D to A, identical to what we saw for the incremental converter previously, except what has changed is the thinking of the quantization noise in the frequency domain. We now have a low-pass filter followed by a downsampler. And if you look at the pictures on the bottom, you see what we have done is we have taken, by using this integrator, we are now noise shaping the quantization noise shown in gray on the bottom. And then after we filter it out, the amount of quantization noise left in our signal band is much smaller. So the breakthrough here, BT being the breakthrough, is to start thinking of quantization noise in the frequency domain, or as signal processing and communications people think about it. Again, I want to repeat this. So if you think about analog computers preceded digital computers, and they were very efficient at solving differential equations. And in fact, the first differential analyzer was a mechanical analog computer that was able to solve differential equations by integration, and around the 1830s. And the most successful of this was a differential analyzer built at MIT by Vannevar Bush and Harold Hazen. And their mechanical differential analyzer were able to solve differential equations with 18 variables. The electronic computers based on op-amps, resistors, and capacitors were well suited for solving these differential equations, as shown on the right, Beckman computer in San Francisco Airport. And just as an aside, I want to stop and talk a little bit about op-amps. So the operational amplifier first started off as a vacuum tube in the 1940s and was built out of transistors in the 50s and ICs in the 1960s. So an op-amp was basically nothing but a DC coupled, high gain greater than 60 dB inverting amplifier. At that point, the positive input was always grounded. So the idea for operational amplifiers came out of feedback theory, and some of the critical theory that had to be developed for feedback theory was done at Bell Labs, basically by Harold Black in 1934, and then formalized with Tellegen paper in 1937. But I also wanted to mention Otto Smith, who was instrumental in making op-amps. In 1938, he talked about the long-tailed differential pair. What does that mean? The differential pair as we know it, with a current source in the middle, is the long-tailed differential pair. He actually invented chopper amplifiers. He's clearly known for the Schmidt trigger, and he established the field of biomedical engineering. And I wanted to chat about him a little bit because he's from Minnesota, where I'm from. Also wanted to talk about a little bit about the term operational amplifiers. So the term was actually coined by John Ragazzini from Columbia, and just as a note, this is Kalman, as in Kalman Filters advisor. So the idea of an operational amplifier was to have an amplifier connected to perform mathematical operations of arithmetic and calculus as using operational amplifiers, and that's where the term op-amp comes from. So, as I was saying, this connection of going from analog to digital, there's a swing. Now, we know, and most young people that grow up know only digital computers, but the real turning point in digital computers came when Claude Shannon finished his bachelor's in math and an EE in Michigan. During his math education, he was introduced to the work of Boole, George Boole. And George Boole has the Boolean algebra. So during his MS at MIT, and again you see the name Vannevar Bush, and he did a PhD in math with Hitchcock. But at that point, what he did was, his master's involved the symbolic analysis of relay and switching circuits. He was able to put Boolean calculus and physical circuits together, and this really sets the tone for digital computers. And though we think of Shannon for his communication theory, which happened much after his PhD work, his master's work really set the tone of the digital computer as we know. And I just want to read the abstract of his master's thesis. And I've highlighted a few letters. So if you see here in his few letters, he talks about the use in the control and protective circuits of complex electrical systems. It is frequently necessary to make intricate interconnections of relay contacts and switches. Examples of these circuits occur in automatic telephone exchanges and so forth. And what you see here is that there is no mention of computers because they did not exist. He basically was instrumental in inventing that field in digital computers. I want to go back and talk a little about analog and digital processing here. So this is work done by Eric Vitos in 1990, and what we're trying to do is the computational effort, or the computational power needed for analog computation and digital computation. So for modeling analog computation, I'm just going to take a Class A amplifier or a Class B amplifier, more efficient, driving a load capacitance, or a single pole amplifier with a particular swing of a voltage called V peak to peak, running from a power supply from 0 to VDD with a frequency of 1 over Fs. So if we go through the equations, we can see that the analog power is given by 8 kT times the frequency times the SNR multiplied by VDD over V peak to peak. And a similar equation for the digital side shows that the digital power is given by some factor m, where is the amount of gates that you have, the energy per transition per gate, and the frequency of operation. So if you look at the graph on the bottom left, we see on the x-axis the SNR, and on the y-axis the minimum power to do this operation of a single pole. And what I want you to notice is the solid line that shows you the amount of analog power used to do this processing. And the dashed lines are the digital power for different digital technologies. And we can see at low SNRs, say between 20 to 40, that analog is 2, 3, or maybe even 4 orders of magnitude better or lower power than digital power. And we see that digital gets better for higher resolution. So I want to kind of consider this and look back at what is going on in here. So if I look at the next slide here, the insight here is one about analog and digital processing, and in particular I want to look at why at low SNRs we take so much power. The digital processing is so much more expensive in terms of power. So let us consider the case where we have a 0 and a 1 shown in the top line. Let it go through the circuit, and after it comes out of the circuit, it is noisy. And we see that the noise is in such a fashion that it's much, much smaller than the values of 0 and 1, or the separation between them. So we have a lot of SNR. So we see that we're wasting SNR. Additionally, I had an insight that I got from Carver-Mead, that once it goes through an inverter, we re-quantize this to a 0 and 1. So what we're doing is we're basically putting a re-quantization in every operation. And it's this re-quantization that is really costing us this extra power. So there are two things that leads to this high power consumption. One is wasted SNR, and the second is the re-quantization. Now as we go to lower supply voltages, we are actually reducing the wasted SNR. So that's one of the reasons why the power consumption for digital goes down as the supply voltage goes down. So clearly what we saw was we went analog computation, Then we went to digital computers, and then that's become the thing that we do all the time. What I wanted to point out in this picture here is that people now recognize that there are places where analog computation may be better. And there are a couple of different computational paradigms that are showing up. One of them is approximate computing, where we use bounded but less expensive solutions using approximate values. And for example, if you use this for k-means clustering, where we take a 5% hit in accuracy loss, we can get a 50x reduction in power. Or in the case of stochastic computing, where the logic becomes extremely simple. A simple AND gate is a multiplier, and additionally it's resilient to some amount of errors in the process. And this is some research done by people in the idea that as we scale down in technology, we're going to get circuits with lots of errors. So for future computation, one of the methodologies that's been presented is stochastic computing. And the third is something that Carver Mead and his students have been working for a long time, where if you look at our brain, it has 10 to the power 11 simple computational low power analog learning techniques that are robust to errors, quite different from the way we do digital computation. And so the ebb and flow of going from analog to digital is kind of coming full circle again. So you see this in this is a cochlear implant from one of Carver Mead's students from Advanced Bionics. So you see this pendulum swing that I talked about between analog and digital in many domains. We actually saw it with servers, then the desktop computers got very strong, and now we have mobiles, phones, and servers again. And this pendulum is something that happens in lots of technology. But my feeling is that the big jumps that happen come from cross-pollination. That means, as we saw from analog and digital communication and in electromagnetic fields. So the point and the giveaway or the takeaway from this talk is that it's important to spend time with people who are different from us. And then the last thing I want to leave you with is that to have fun and take time to reflect on what you do. Well, thank you.